Okay, imagine this. You're playing with fridge magnets and you notice how they stick together. It's like magic. They hold up photos and notes and somehow just work. But what if I told you there's actual science behind this? Enter the Ising Model, a super cool way to understand how tiny magnetic interactions create order or chaos. Alright, picture this. Each arrow is like a tiny magnet, or spin as physicists would call it. It can point up or down. These spins like to match with their neighbors. If their body is pointing up, they want to point up too. If they don't match, they get all grumpy and unstable. Magnets work because most of these tiny spins inside are aligned. But what if we crank up the heat? Boom! Chaos! The more heat we add, the more disorder we get. And if we go over a certain temperature, everything goes random. No pattern, no order. But what if we cool it down? The arrows start to agree again. This is called a phase transition. The same thing that happens when ice melts into water or iron turns into a magnet. Now, let us consider this grid as our system. As a system, it has a value for its energy. We call it the total energy of the system. Now let us zoom in on this region of our system. We can see that many of the arrows align. Now, what does this mean? This means that this region has low energy. Everything is organized. In short, the arrows are very happy. Now, let's take a look at this region. In this region of our system, we can see that many of the arrows are misaligned. What does that mean? It means that the arrows tend to be grumpy because they are all misaligned. It means that this region has high energy because the arrows would want to spin just to be aligned and be happy again. Question: how will we measure the total energy of the system? Pause and think about it for a bit before proceeding. Ang hirap naman, buti na lang alam ni Wilhelm Lenz at Ernst Ising kung paano gagawin. Now, what does each of the variables represent? We have E for the total energy of the system. Low E means that the arrows or spins are happy and stable. High E means the opposite. We have J for the interaction strength, where basically it is how much an arrow cares about matching their neighbor. Positive J means that they want to align, while negative J means that they want to be opposite. The summation symbol means that we add up the interaction of each pair of arrows or spins. And now, do you see that the IJ part of the summation symbol? That means that we only count the neighboring pairs. And lastly, we have S sub I and S sub j, which are the individual spins. They can have the value of +1 pointing up or -1 pointing down. Now, let us try to visualize the Ising model using a simple problem. Here, we introduce a 2x2 matrix with these elements. First, let us calculate the energy step by step. If we have J is equal to 1, we have the following equation. We simply evaluate this to get E is equals to 0. This only means that the system is not too chaotic, but is also not too ordered. Now, what if we were given a large set of spins? Would it be practical to solve the total energy requirement of the system manually? Sige nga, joke lang. Luckily, we have our friend Python to help us solve large systems. So get ready, because in the next video, we will show you how to write it all in Python.